Good afternoon. Okay, we're going to continue on with the CAP-M model. CAP-M continued. And where we stopped off was the implications of the CAP-M. And let's see where we are on that. We just started giving a third implication. And this important implication is the following. It says the risk premium which is the reward for bearing risk, of any asset I is proportional to the risk premium of the market portfolio. M. We call that market portfolio. And the way this does, a measure of the risk premium of asset I why don't we say this? The way that the risk premium of asset I varies with respect to that of the market portfolio is given by these beta i's, by beta I here. This is just beta sub I. Okay. And the way it's done is the following. We can look at this graphically. All right, we'll have the following. Let's not do this graphically first. Let's do this. Let's give the equation first. The CAP-M equation. We'll do graphically in just a second. this shows exactly how the risk premium varies. It says that RI minus RF. So we take the rate of return on asset I minus the risk-free rate equals beta I times RM, this is R bar, M, minus RF. And this is equation 7.2, page 177. Okay, so this is our CAPM equation here. Okay. Okay, and if we look at this, what do we see? This is the risk premium of asset I. And what that equals is the amount, the proportion or amount of the expected rate of return in excess of the risk-free rate. Okay, so our risk premium is just what we get for bearing risk. And over here, on the right-hand side, we have the risk premium of the market portfolio. So, of course, you can solve for the expected rate of return of any asset by simply moving the minus RF to the right-hand side. Asset I is simply, we'll take that R bar I equals RF, our risk-free rate, plus beta I times R bar M minus RF. Okay. So this is all we need to do to solve for the expected rate of return of any asset. Now, what about beta I? Beta I, if beta I is greater than 0, it means that the risk, the expected rate of return is positively correlated with that of the market. Portfolio. In fact, if beta I, let's make sure this looks like a beta. If beta I equals 1, then asset I and the market are in lockstep. The market move in lockstep. What we mean by that is that if the market goes up 25%, then asset I, expected rate of return, should go up by 25%. If beta I equals 0, beta I equals 0, then asset I's expected rate of return in the markets let's say RM are not related at all. So the market could go up and asset I's could do anything. It could go up, it could stay where it is, or it could go down. Now if beta I equals -1, then the asset I's expected rate of return and the market's rate of expected rate of return are perfectly negatively correlated. So what this means that if the market goes up 25%, then the expected rate of return on asset I should go down 25%. Okay. So knowing the beta I's is all we need to know for the CAPM model. Knowing the values of the beta I's we can calculate R bar I's for all assets. Okay. This gives the CAPM model a significant computational advantage over the mean variance approach. And we'll say, why? Why is this? Okay, let's answer that question. In the CAP-M approach, we only need to compute n beta i's plus we need r bar m, the expected rate of return on the market portfolio. So we need n plus 1 computations. Whereas in the mean variance approach, we need to compute, we have n means plus n variances plus n times n minus 1 over 2 covariances. Okay. The 2 here comes from the fact that sigma ij equals sigma ji. So once we compute sigma ij, we automatically have sigma ji. Okay. And we have n times n minus 1 covariances because there are n i's and n minus 1 j's that are not equal to i's. Let's do this. N i's, and we have n minus 1 j's not equal to I. Okay. Now, what does this come out to be for, say, for this? If n is large, this is a distinct advantage. CAP-M, a distinct computational edge. Okay. For example, say that n equals 1,000. So you have twice the number of stocks in the S&P 500. By the way, the market doesn't look good today. It didn't look good yesterday. Or maybe out in May and stay away was a good idea. But then you get what we get for mean variance. we have what? We have equals 2 times n plus n squared minus n over 2. We'll say the number of mean variance computations. And if you calculate this, this is equal to 501,500 values versus 1001, let's write that correctly, values for our cap M. Okay. So you can see here, it's like a 500% decrease in the amount of computations. If you would take the Russell 2000, 2K, it would be, the computation advantage would be even more. Okay, now, how do we calculate beta I? Beta I is critical. Beta sub I, for asset I. We'll say that beta sub I equals the covariance of asset I with the market portfolio over the variance of the market portfolio. This is equation 7.3. So to calculate beta sub I, you need the variance of the market portfolio, and you need the covariance of asset I with the market portfolio. Okay. And this is, how is this derived? Should have had another thing here. I don't see it. Is equation 7.3 derived. Okay, let's look at it. First, we take a portfolio made up of alpha proportion of asset I of alpha proportion of asset I, where alpha is greater than or equal to 0 and less than or equal to 1, and 1 minus alpha proportion of the market portfolio. Okay. And so we get something that looks like this. We get an R bar P. Oh boy, that's not very straight. Sigma P. And then let's draw this. This is efficient frontier. For asset I. And then what do? We go from the risk-free rate. Let this be the risk-free rate. I'll put that with a capital F there. I think before we use the lowercase. And then we'll draw this line here. Here. This is, right here is the market portfolio. Where alpha equals 0, we have no proportion of asset I in it. And this other thing here, the straight line, is called a capital market line. Okay. Now, what else do we do? We see that. Let's keep that out. Okay, then we do a little tricky thing. We say that, secondly, we equate the slope of the capital market line and that's the line that passes through M. And also starts at the risk-free rate. And the tangent to our portfolio at alpha equals 0. And at alpha equals 0, this is corresponding to M. To our market portfolio. And so what we do is the following. We evaluate the following. We take the partial derivative of the expected rate of return, P, over the standard deviation in P, and evaluate that at alpha equals 0. So we have that for our portfolio, but we evaluate it at alpha equals 0. And if we do that, we see we get the partial derivative of R bar P over d alpha over the partial with respect to sigma P over d alpha again. And this is evaluated at alpha equals 0. Okay. Now, let's recall the following, that R bar P equals alpha R bar I plus 1 minus alpha R bar M. Remember, here we have alpha, we're evaluating this at alpha equals 0. And standard deviation of that portfolio is equal to alpha squared sigma I squared plus 1 minus alpha squared sigma M squared plus 2 alpha 1 minus alpha sigma IM. And we take the square root of that. Okay. Where sigma IM equals the covariance of asset I with the market portfolio. Okay. Now let's assume that there are n assets in the market. Our market is M. Okay. Then, what do we have? The covariance of asset I with M is equal to the covariance of Ri, Rm. Okay. That equals the covariance of Ri, and let's look at the covariance of Rm. We can say, now we have to take the covariance with every asset in M equals 1 over n to n of Wj R bar j. And this equals what? It equals the sum of the Wj, j equals 1 to n assets in our portfolio, the market portfolio, times the covariance of Ri, Rj. So the covariance of I with M is simply the sum, j equals 1 to n, of Wj, the covariance of I and j. Well, this is where we wanted to get here. Okay. So let's take an example. Let's take an example. So, for example, if the market is made up of two assets, if the market is composed or comprises two assets, and we'll call these assets 1 and 2, then what do we get? We get the covariance of asset 1 with our market equals W1, the covariance of 1 with 1, plus W2, the covariance of 1 with 2, equals W1 times sigma 1 squared times the variance, because 1 with 1, take the covariance of 1 with itself, you just get the variance, plus W2 covariance of 1 and 2. And we get that the covariance of 2 with M equals W1 covariance of, let me write that out, covariance of 2 with 1 plus W2 covariance of 2 with 2. Okay, let's write that. Now, what do we know? We know that the covariance of 2 with 1 equals the covariance of 1 with 2. These two guys are equal. So this equals W1 covariance 2 with 1 plus W2 sigma 2 squared. Okay, so that's easy to calculate what these covariances are. Using this, we can show the following. We can show that the variance of the market portfolio equals W1 sigma 1 2 plus W2 sigma 1 2. Since we have that sigma m squared equals W1 squared sigma 1 squared plus W2 squared sigma 2 squared plus 2W1 W2 sigma 1 2, and we have that W1 sigma 1 2 equals W1 times W1 sigma 1 squared plus W2 sigma 1 2. And this is just the covariance of 1 with M. Okay. Okay, let's see what else we need here. let's look and see what else we need here on the CAP-M. Okay, we'll have it there. Okay, now, let's say something else. The next thing we're going to do, we're going to look at this is the pricing form. Next we're going to look at the pricing form of the CAP-M. We'll do a little more on the CAP-M. The pricing form of the CAP-M so we have a few more things to finish up before we finish the CAP-M, and we go into so-called factor models. In a factor model, what do we have? We want to relate the expected rate of return. Let's write this out. These relate asset I's R bar I to a number, say greater than or equal to 1, factors. And these factors can be exogenous. They couldn't be like the CAP-M model is a one-factor model where the factor is the market portfolio. Or they can be things that relate specifically to the asset. They can be like things like price-earning ratio. Why don't we put something in here that the CAP-M is a one-factor model or single-factor model. With the factor being the risk premium of the market portfolio. Okay. Okay. So we're going to go into the factor models. We'll finish up CAP-M and go into our so-called factor models. The CAP-M is just a one-factor model. Okay. I think I'm going to stop a little bit early today and give you guys a break. And I think we're going to have the test the week after we come back from break. Okay, and I'll discuss the test. Actually, I'll try to discuss the test before we go on break. So I'll tell you what you're responsible for. Okay, Thank you very much. Hope you have a good afternoon. Try to keep cool. It's hot here in West Lafayette. And we'll see you tomorrow. Thank you.